In the previous tutorial, I showed you how to solve the following question. Given that x was bigger than 0, find the two smallest value of x in radians for which a 3 tan 2x plus 1 was equal to 1. And we went through the solution process. So first of all, we rearranged for tan 2x plus 1 was equal to 3, and then did the inverse tan. So we had 2x plus 1 was equal to 10 to the minus 1 of 3, 0.322, 36464, and 6605. And that would give us the solutions of inverse tan 1 over 3. But because it's been shifted by 2x plus 1, we then have to rearrange for x. And what we found with the three solutions is that one of them was not valid because the criteria was that x was bigger than 0. So we can see here that 3.22 minus 1 would give us a negative number and therefore would not be valid. So we only got the two solutions in the end, which was 1.23 and 2.8. I also mentioned that we were going to program this in the next tutorial, and that is what we're going to do. So we can see here that this is the program solving the following equation that we've just discussed. 3 tan 2x plus 1 is equal to 1. The criteria that x has to be bigger than 0, and it's the two smallest solutions. Now, for any model, mathematical model that we're doing, and mathematical models can be very, very small in scale and very, very large in scale. And well, whenever we do this kind of thing, we are basically creating a very, very small mathematical model. And it requires three things. It requires input, the algorithms to solve, and then the output. And let's have a look at each part of the code to see which is which. So here we have the inputs. This is what the user will put in. And so we've got there and inputs. And you can see some commands here. So we've got input, which makes sense. That's what we're the user to do. And we're telling the user the A coefficient. Now let's talk about that a bit more. For the equation we're solving, 3 tan 2x plus 1 is equal to 1. This is not a standard trig equation, like a nice simple one, like sine x equals a half and that sort of thing. It's got a few more components to it, like a shift and a stretch. So what we've got is that our A coefficient will be 3, our B coefficient will be 2, our C coefficient will be 1, and our D coefficient will also be 1. And we're just telling the user what you type in will be the A coefficient, what you type in with the B coefficient, and so on. And we have this float there. And the reason why the float's there is quite simple, is that we don't want the users who put in anything that is not numerical. So if the user, for example, put in pancakes, then it's going to error, which is good. That's what we want. So we always want the code to be robust against user error. Now, moving to the next part, this is the solving part, and it's split into two parts. So here is the part where we rearrange for inverse tan. So we get 2x plus 1 is equal to inverse tan. And in our case, it was 1 over 3. But what we've done with the input is that we've made it general. And again, that's a good sign of a good mathematical model, is that it's general. It doesn't just work for the numbers that we happen to have for the question. So no matter what they put in for A, B, C, and D for solving, it's still going to work. So in our case, like I said, D would equal 1 and A would equal to 3. And I'll just put here the solving process so we know the whole thing. Then from there, we've got x1 is equal to y1 minus c over b, and it repeats for x2 and x3, which makes sense because, again, if we rearrange this, we're going to get x is equal for inverse tan, which we've already defined as y, minus 1 all over 2, which the computer will read that as where y1, which is 10 to the minus 1 a third. So y1 minus c, so our c in this case is 1, divided by 2, which is our b. Cool. Now, let's run this, which is, and when we run this, we will get an output because the print gives us our outputs. We talk about the three phases. We've got the output phase here, and it's going to print x1, x2, and x3, which is good. So let's just run right now. So A coefficient. So again, just to test our code, we want to make sure that the output of the code matches what we know the correct solution is. So A coefficient is 3. Our B coefficient is 2. Our C coefficient is 1. And our D coefficient is 1. Apparently it's D. So that would have errored if I'd put D instead of 1. Okay. And we're going to run this. Now, we already have a minor problem here. And the fact is we get the 3 solutions. However, we know that the question criteria was x is bigger than 0. So the first solution here is invalid. Now, how do we solve that? Let's just get rid of print 1. And we're going to run that again. A coefficient would be 3, B coefficient 2, C coefficient 1, and D coefficient 1. And there we go, we get our 2 solutions. And we know that they're the same 2 solutions that we got when we solved it on paper. So therefore, this is our code working. However, there are a number of problems to this code, and we're going to discuss that right now. So the number of problems are this, and there's actually more problems than this, but I thought I'd just highlight this as the main ones. So we see here that rather than the computer deleting the x1 solution, I had to. So that's never a good sign. The user should not be doing anything. The code should automatically go, x1 is invalid because it's less than 0, it's gone. Which kind of links to the second point as well, where it will only work if x2 and x3 are valid solutions. So let's say I mentioned earlier that the code is good because I can put in any value of A, B, C, and D and it will still work. But it actually won't, in the sense that what if x4 is a solution? What if it had 3 solutions? What if it had 5 solutions? What if it had 10 solutions? So that's not going to work for any other situation apart from this specific question. And linked to that, there's no specified option to modify the domain. So again, we want it to work more generally. This only works specifically if x is bigger than 0. And even then, I had to manually delete the solution. So we want it to work for any domain, not just that one, if we want it to be more general. So the next one, solutions are only increasing. Now, what we mean by that is when you're trying to find paired solutions for trig functions, you're adding 2 pi to them. Now, you can also go backwards. There might be solutions lower than the principal value, not higher than the principal value as well. So we've only done ones that are increasing from the principal value, not the lower ones. Next one, no ability to check if solutions are valid. So again, this case only works for that particular question, not if the numbers were modified. No functionality for sine and cosine. So, we've only got the 10 algorithm, not sine and cosine. And also no random solution. This one's a minor one, but our solution inputted quite a few decimal places. We only want it to be 2 or 3. So in the next tutorial, we're going to address all of these limitations and create a code that will solve any sine, cosine, and tangent trig equation.